1990 doesn't seem to be that far in the past, but our Earth is no longer the same. According to the IPCC report, in 2023, global temperature have increased by 109 degrees Celsius, with greenhouse gas emission rising 54% since 1990. The rapid increase is largely driven by the human activity, including energy consumption for cooling. One of the biggest contributors to this problem is the use of foreign gas in refrigerant. In 2023, Europe alone consumed 75 million tons of CO2 equivalent foreign gas. These gases, such as FC and CFC, have a global warming potential of 6,410, making them highly determined to the environment. The property sector, particularly the commercial building, relies heavily on air conditioning. In 2022, ISPO-related emission reached 439 kg per unit, highlighting the need for a more sustainable cooling solution. Before refrigerant, cooling system relied on evaporative cooling. However, traditional evaporative cooling is limited by the wet bulb temperature. It requires relative humidity, which can cause discomfort and damage sensitive electronics in office. This problem raises a question: how can evaporative cooling be improved?
That is why I, Alexander Dewanto,
and I, Daffa from SMAN Negeri 3 Malang, address this problem with our research. A sustainable desiccant evaporative cooling system based on polyurethane graphene oxide, nanocomposite with solvent exchange method, synthesis, composite characterization, and performance analysis. We choose polyurethane because it is a promising material for cooling pads, due to its high flexibility and mechanical strength. However, polyurethane has several limitations: low thermal conductivity, limited water absorption, and thermal instability at high temperature, which make polyurethane not suitable for evaporative cooler use. So, what's the solution? One effective approach is modifying the material to enhance its properties. Graphene oxide is used because of its excellent thermal conductivity and hydrophilicity, which improve water absorption and cooling efficiency. Objectives of this research are characterizing the synthesized graphene oxide, optimize and evaluate polyurethane graphene oxide foam, design the evaporative cooler, and analyze its system performance.
Our research was conducted from October 2024 to January 2025 at SMAN Negeri 3 Malang, Erlangga University, and ITS University. The research method and flow are as shown, which will be explained in detail further in the presentation. The synthesis of graphene oxide or GO are as follows. Graphite and sodium nitrate were mixed in sulfuric acid with an ice bath. Potassium permanganate was added slowly, keeping the temperature below 20 degrees Celsius and stirred for 3 hours. Oxidation was completed with distilled water. Then the reaction was stopped with hydrogen peroxide. The mixture was centrifuged, dried, ground, and purified by washing with hydrochloric acid and distilled water to obtain pure GO. To confirm the success of our GO synthesis, we conducted FDIR and XRD characterization. FDIR analysis identified key functional groups, including hydroxyl confirming oxidation and C-double bond C stretching, proving graphene's aromatic structure. XRD analysis further validated our GO synthesis. A peak at around 11 degrees revealed increased interlayer spacing, showing oxidation success. Peaks around 37 to 44 degrees, highlighting the need for better purification. A small peak near 20 degrees confirmed some structural variability within the GO layers. Foam synthesis aims for higher saturation, but GO doesn't naturally bond with polyurethane. To solve this, we developed a novel solvent exchange method with the thought process of these 3 steps. Step 1, confirming the need for a solvent. Acetone-based foam showed the highest water absorption, proving a solvent is necessary. Step 2, testing different solvents. Acetone caused structural collapse, water prevented expansion, and chloroform evaporated too quickly. Isopropyl alcohol, or IPA, was the most effective, yielding the highest water absorption. Step 3, optimizing IPA use. Since IPA removes some blowing agents, 2 weight% and 3 weight% distilled water was tested. The 2 weight% addition proved best for structural stability and water absorption. The final synthesis methods are as follows. Mixing polyol with GO and IPA. After stirring and heating, 2 weight% distilled water was added for blowing agent, followed by the addition of isocyanate. The foam then underwent pre-treatment procedure with 24-hour water immersion to enlarge pores and increase surface area. It's shown that FDIR confirms GO increased hydroxyl groups, enhancing foam hydrophilicity. To confirm the impact of the added GO, the hydrophilicity is then confirmed via contact angle analysis that show a reduction from 101 degrees to 68 degrees. Microscopy test was done to see the effects of pre-treatment. It revealed a 46.35% increase in pore size and 12.8% increase in porosity. These improvements boosted water absorption, with polyurethane graphene oxide foam or PUGO foam retaining 333% of its weight, outperforming traditional cooling pads. And here's how our system works. Our system draws in ambient air with a fan, passing it through a desiccant wheel that absorbs moisture and lowers well bulb temperature isothermically, creating dry air. The dry air then moves through the Pugo evaporative pad, cooling via heat transfer and evaporation. This process lowers the dry bulb temperature by raising the humidity, making it an adiabatic process. Cool humid air is then expelled by another fan to prevent recirculation. It is shown that the system achieved optimal temperature. Moisture content continuously decreased due to isolated airflow. Psychrometric analysis shows slight enthalpy changes due to heat from the desiccant wheel. It lowers WBT, reducing humidity, while DBT rises slightly but remains isothermal. Further cooling increases humidity near saturation, confirming the efficiency. Cooling capacity reached 1,315.71 BTU per hour, with potential improvement through better aerodynamics as airflow dropped 12.54%. Energy efficiency analysis showed 224.24 watts power consumption, achieving an energy efficiency rating of 5.87 BTU per watt hour, far exceeding conventional AC.
Our research confirms successful GO synthesis through modified Hamer's method and Pugo for synthesis using IPA, enhancing hydrophilicity and water absorption to 333%. The Pugo evaporative cooler with a desiccant wheel and nichrome heater achieved a 5 to 7 degrees Celsius temperature drop, 1350.71 BTU per hour cooling capacity, and energy efficiency rating of 5.87 BTU per watt hour, far surpassing conventional AC. This result proved Pugo foam as an efficient material for evaporative cooling. It is recommended to maximize improvement, including optimized GO purification, enhancing pad aerodynamics, and scaling the system. Collaborative with industry is a key for better result.